Okay, I think the meeting has started. The recording has started. I hope everyone's having a good summer so far. It's been super fire. And experimenting with a little bit of a different background just to represent that we're in summer and we're having a chill time. And so I wanted to get ahead with the lecture series, and I'm going to get started with the signals and systems. This was a very well requested course because the computer engineering people take it, the electrical engineering people take it. So I just thought it would be a good idea to get started on it soon. And this is going to be a fun thing to teach because I love that class. I love the math that goes behind it, Fourier transforms, Laplace transforms. I love that. This is going to be fun. And I think there's way more content mathematically to cover here. So sometimes the lectures, I want to split it in parts probably because we'll have a lecture one, part one, lecture one, part two, maybe part three, depending on how tough the topic is. So that's pretty much it. And I'm just going to get started with it, to be honest. Just want to, so for anyone who's trying to get a head start in the core signals and systems, it's a challenging class sometimes for some people. So you know, learn the content before you even start the course. So signals and systems, lecture one, part one. So introduction. What is a signal? Basically, you need to understand a signal. It holds some kind of data. All right, it could be a voltage, current, some type of data, and it is a function of time. Okay. Now we have in signals and systems two different styles of time. We got continuous time, where it's continuous for every single number on the real axis for real numbers, and then we have the other one, which is discrete time, which is only integer values at different points. But we're gonna see more on that later. Now, what is a system? A system is anything that takes an input and then gives you an output. And usually it's modeled by differential equations and convolution integrals. Differential equations, I think the electrical engineering people, they have taken it, so they have a little bit of an intuition behind it. Computer engineers, depending on whether you took the class sooner or later, I'm not quite sure, but I think a lot of computer engineers don't take differential equations until they take signals and systems. So that can be a little bit challenging. So you could go and maybe research about differential equations on your own, or but it's for the first part of the course, it's not heavily important. You can get away with it. But for the second half, when you start looking at systems, that's when differential equations are very, very important. So we have, like I've said before, two types of signals: continuous time and discrete time. And we have an example, very crude example here. So we got our x-axis here that represents time, the y-axis that represents the signal as a function of time, and you can see that this signal is continuous for all values of time from negative infinity to positive infinity. Now, discrete time signal, we have a variable n. So very important to notice when you're representing a continuous time signal mathematically, you're going to use round brackets and you're going to use the alphabet T for time. When you're describing a discrete time signal mathematically, you're going to use the variable n, and then you're going to use square brackets, so x of n. So that's your discrete time signal. So very important to have that switch in your head, so then you're not confusing yourself down the road. And now you can see here on my time axis, I have different points: -2, -1, 0. That's because discrete only works for integer values. And at every integer point, you have uh, an amplitude to represent your signal. So that's basically the two types of signals. Now, you transformations of the independent variable. So when you have a signal, whether it's in the continuous time domain or discrete time domain, um, you want to be able to manipulate that signal. You want to be able to scale it. You want to be able to shift it. You want to be able to reflect it. Whatever the case may be, you should be able to manipulate these signals mathematically and graphically as well. So we're going to start with some graphical manipulations here. And you might have seen this very similar if you went to high school in Ontario um, in grade 10, where you had like parabolas, you had to stretch it, you had to shrink it, you had to flip it. So maybe you need to tap into that muscle memory from then because it's pretty much the same thing, but we're just not calling it a function. We're calling it a signal, but you're doing the same things over and over again. It's just that these signals, these functions, are a little bit more complicated in their mathematical expressions. Okay. So I'm going to start with a shift. So this is your original discrete time signal x of n, and you can see the time labeling here. And if I shift the signal by some integer value n0, this is what happens to my signal. Now you can notice this V kind of shape over here, which starts at 0, this V shape. It's shifted now by n0. So this V shape will now start by n0. Okay, and then that's your signal shifted in time. That's for discrete time. And the same thing over here. We have this kind of shape, and you can notice that we have a little bit of a peak going on here. Well, the peak really is here, but a little bit to the left we have a little bit, lower than the peak. We have this point. This point is shifted by t0, and now the point is over here. So all we did, we shifted the signal by t0. Now you might notice by shifting the signal by n0 or t0, we're adding a minus sign here. And for the, this is math. This is what happens if you go on Desmos and then you put a scaling factor. You have x of 2 minus, or x of t minus 1, okay, and then or x of t minus b, and then you try to scale the b. You will see that's what happens. But we're electrical engineers, we're not mathematicians. So what I want you to imagine is when you have a scale minus n0, all right, so you have a signal of time and shifted by n0, x of n minus n0, that minus in your head, you should try to think about it as lateness. So your signal is late. How much is your signal late by? It is late by n0, okay? So initially you had your signal here, but let's say you put it through a system, and at the end you're measuring that signal again, but you're like, oh, nothing happens, nothing happens, nothing happens. And you check the clock, it's at n0, and you see something. Your signal was late by n0. How do you represent that mathematically? X of n minus n0. So that's a little bit of a physical intuition on how you can think about it. Okay. Same thing, reflection. Reflection is basically like a mirror flip. That's pretty much everything there is to it. So you have a signal that looks like this, and then you flip it. This is the x of t right here. This axis, it acts as a mirror, and then your signal is now reflected. So scaling is a little bit tricky because it's the opposite of what you think it is. If you want to make a signal shrink, you want to multiply the time axis, right? You want to multiply it by your factor you want to shrink it by. If you want to enlarge your signal, you want to stretch it out, you want to divide the coefficient of your variable of your independent variable. So you have x of t. Let's say you want to make that signal shrink. You're going to go x of 2t. That's going to make the signal shrink, okay? Because you're multiplying the time by 2, so it's going to make your signal shrink. Now, if you want to enlarge your signal, you're going to go x of t over 2. So it's a little bit difficult to think about at the start because I struggle with that too. Like you just saw me have to take a minute for a sec. But multiplying is going to shrink your signal, and then dividing is going to enlarge your signal. And there's a certain order of operation we want to follow when we're doing these graphical operations. First, you want to shift, and then you want to scale and reflect. Now, reflection is pretty much the same thing as scaling. Okay, if you think about it, all a reflection is just scaling your function by a negative sign. That's all it is. All right, so you have x of t, and then you scale it with a negative sign. You have x of minus t. But that we call it reflection because it's in your head. You can if you call it shifting, or if you would call it scaling, then your head is kind of thinking about stretch and shrinking. But if you call it reflection, you know that something is flipped. So that's why we have a different name for it. Now I'm going to go through an example. So we have a given signal x of n, and then we want to plot x of 2n plus 1 and x of n over 2 minus 1. So how do we plot this? First of all, we're going to shift, and then we're going to scale and reflect. Okay. So now, first, what you're going to do is you want to do the shifting part. So over here, if you look at this part, this is the scaling, and then this plus 1 is the shifting. Okay, so we're just going to start by shifting. So you're going to ignore that 2 for a second. This is x of n. We're going to find out what x of n plus 1 is. Okay, so all that's going to happen is everything's going to move to the left by 1. And I noticed earlier that minus sign represented that your signal was late. Okay, but how much? By n0. Here, you have a plus sign, which means your signal is early. That means it's going to go to the left because it is early, right? It is early by 1. So everything here is going to move 1 step to the left. You're going to have something like this. You see what I mean? And then if you take everything here, you shift it to the left, this is what you have. Okay, now if you want to find x of 2n plus 1, again, remember what's going on here is you're multiplying. So that's going to shrink your signal. So that means you need to divide to counteract that effect. Okay, so this is your scaling here. You're going to take 4, you're going to divide by 2. It's kind of like algebra. So if you think about it, 2n plus 1 equals 0. So first, you're going to minus 1 on both sides. So you're going to do the, let me do it piece by piece. So let's say you have here 2n plus 1. 2n plus 1 equals 0. And then you have 2n equals minus 1. So you start by subtracting your time line, your time axis by minus 1. Okay? So 0 minus 1 is minus 1. So this point becomes here. 1 minus 1 is 0, so this point becomes here. Okay, 2 minus 1 is 0, 2 minus 1 is 1, so this point gets here. Do you see what I mean? And then after you're doing the shift, you have 2n plus 1 equals 0, 2n minus 1, okay, n equals to minus half. Okay, but you've already done the minus part, you've already shifted it. Now all you need to do is multiply the x-axis or the time axis by half. So that's why we're doing the halving here. So multiplication and division, these terminologies can bug your head a little bit. So all you want to do is you want to take this, set it to 0, and follow the order of operations here. Okay, it's just bed mass in a graphical form. So that's all we're going to do. Now we're going to take every single x value here, or n value I should say, value of time, and we're going to divide it by 2, because as you just seen, 2n plus 1 equals 0, so n equals to minus half. All right, so we're going to multiply it by half. So 4 times half is negative 2. And then you do that for every single point. Now you're going to notice that at some points you have fractional values. This is a fraction, this is a fraction, this is a fraction, this is a fraction. But when you're dealing with discrete time signals, everything is an integer. So what happens at all of these fractions, you're going to put a 0, right? Every single fraction becomes now a 0. And everything else that is not a fraction is now going to remain. So for example, this does not exist anymore. Does not exist, does not exist, does not exist. Now everything else exists, but where you're gonna plot it in the time domain changes. Because listen, this was a 0, and it was a 0 at minus 4. But you times that minus 4 by half, so now it's at minus 2. So your minus 2 will have a 0 here. So you see what I mean? Now next up, we have this minus 2, which is a 0. Minus 2 times half is minus 1. So now you're gonna have a 0 at minus 1. Okay? Now at 0, you times it by half, it's still 0. So at 0, you have a 1. You see what I mean? Now this 1, it got divided by 2. So this does not exist, it's a 0. Now this 2 right here, you times it by half, you get 1. Okay? And what is the value here? It's 1. So instead of plotting it at 2, you're going to now plot it at 1. So that's why you have a 1 here. So that's how you shift, and that's how you scale your signals. Okay? If you want, you can go back and then try to do it on your own again. So that was the first function, the first signal we tried to plot, and now we're going to plot the second one. Okay, now notice over here, I want you to kind of pause the video and then try to do this one on your own, and then come to fact check your result here. But assuming you've done that already now. So we have this signal. First off, we're going to start by shifting our signal by minus 1. So what does that mean? Is we have a minus sign, our signal is late, which means everything will be moved to the right by 1. Okay, that's a graphical way to think about it. So I'll take whatever I have going on here, I'm going to move it to the right by 1. Okay, now notice I have, if I do the math for this one, we have n over 2 minus 1 equals 0. So first thing we got to do, we got to add 1 on both sides. The second thing we're going to do is we're going to multiply both sides by 2. We need to multiply by 2 to get rid of that 1 over 2 factor. So every single x value here is going to be multiplied by 2. Now, when you're multiplying an integer by another integer, the answer will be an integer, okay? That's just common sense, I guess. So now you're going to notice how it's going to scale, how it enlarges the signal. You see over here, what happened here is we have a signal, and then we multiplied it, the coefficient of n multiplied by 2. So multiplying shrunk a signal. Why? So you might notice how this one is fat and this one is kind of skinny. It's because we lost a couple of points in the process. Why? Because some of our time values, they turn into fractions, which don't exist in discrete type signal. So that's how it shrunk, because we lost some data points, okay? And then multiplying or dividing, dividing your, let me rephrase, multiplying your variable by a fraction 1 over 2 is going to enlarge that signal, because you need to multiply it by 2 to get rid of the 1 over half factor. Okay, so you have 4 times 2, which is minus 8, 3 times 2, which is minus 6. You keep on going, blah 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 blah. You do for every single one, and then all you're going to do is you're going to plot for every single point. So at minus 8 we have a 0, at minus 6 we have a 0, at minus 4 we have a 0, At -2, we have a 0. Now, you might notice here, because we multiplied, we lost a couple points. So, for example, we have -2, we have -4, but where's -3? You're just going to assume it's 0 because it's just 0, okay? That's all it is. So, you're going to do -3, 0, -2, 0, -1, 0. You keep on going. And then here, you have a value for the signal, but you took the x value and you multiplied the n value multiplied by 2. So now it's at 2. So the 0.5 is now at 2. Okay? 2 times 2 is 4, so now we're at 4. And the value is 1, so it's here. 3 times 2 is 6, so it's here. And then and then the value here is 1. So that's how you keep on going, and that's how you get your final signal. Okay? So this is lecture 1, part 1 of signals and systems. And I hope you enjoyed. And I'll be posting more lectures soon.